Yeah. So sorry for that. So I thought I'll spend one more lecture on the basics of integrators and differentiators. In the previous lecture, we spoke about some non-idealities. How does integrators and differentiators behave in the presence of offsets, in the presence of noise? And then we did some modifications to the ideal integrator and ideal differentiators to make them more practical. Okay. So in this lecture, I'll just solve some one or two interesting problems on different integrators and differentiators. We will look at some different ways of realizing the ideal integrators and differentiators. And then the more important thing, which is very useful, is to understand how the integrators and differentiators behave when we apply step inputs and pulse signals. Okay, when you apply periodic pulse trains, it's a very useful uh, signal, but especially they are such circuits are often used in circuits called function generators. So you must have used function generators. They will have some form of circuits like that. Today we have more digital function generators, which do a lot of processing in digital domain. Okay, so I'll just talk about that. And yeah, so far I'll just show these two circuits, since I think you're aware of these two circuits here. This is an ideal integrator. This one is an ideal non-inverting integrator. So what is the transfer function of this circuit? Do you guys remember this? What is the transfer function of this circuit? Do you remember that? So start from here, right? So this circuit is a negative feedback. So that when you find the transfer function at this point, what will that be? 1 by 1 plus SRC. Multiply it with by the transfer function of the non-inverting configuration, which will be 1 plus Z2 by Z1, 1 by SRC. So if you write this, you will end up getting 1 by SRC. So this one is a non-inverting integrator. Okay. So here you get a minus 1 by SRC sign. I'm assuming the op amp to be ideal. So you get minus 1 by SRC here. The same way, this one here is a inverting differentiator. So you take this impedance and divide it by this. So you will get R by 1 by SC with a minus sign. So you have minus SRC. So that's the ideal differentiator. Now this circuit here is just an inverse of, I've just replaced interchange capacitors and resistors. Okay, then you get a differentiator operation. So if you see the transfer function to this point, if you take a high pass filter R, C and R, the transfer function to this point will be SRC by 1 plus SRC multiplied by, now you are, once you reach this point here, this circuit is a inverting, non-inverting amplifier, and the gain of this non-inverting amplifier is 1 plus Z2 by Z1. 1 plus Z2 is the feedback resistor, R divided by 1 by SC, so it will be SCR. So these two terms will cancel out and you will get ideal non-inverting differentiator using, yes. So you'll get ideal non-inverting differentiator using a single op amp. See, otherwise we said we will need one more op amp. You have to add one more op amp at this output to invert the sign, from minus to plus. Same way, if you want to get a non-inverting differentiator, I had to put one more negative sign here. Okay. I just had to put one more negative sign with a gain of minus R and plus R, with a two resistors of same value. So this will give me a gain of minus 1. Okay. So this is where we realized it. See, this holds true for single-ended circuits. For differential circuits, if you have fully differential circuits, we can realize inverting or non-inverting using a single stage itself. You don't even need to go for a complex structure like this. You don't need to go for this. So a differential integrator will look something like this. So you'll have two resistors and two capacitors on either side. Okay, the output will also be differential. If your output is differential, the circuit will look something like this. So if I apply positive input here, if I take the output across it as it is, so here this is, let me put it minus here. This is plus. So this is plus, this is minus. So if I take the output as it is here, I will get an output of minus 1 by SRC. If I want plus 1 by SRC, I should just flip the outputs. That's it. If I flip my output, I'll get a negative inversion sign. So that's the other advantage of differential circuits compared to a single-ended. Polarity flipping is very simple in differential circuits. Okay. So now I'll take a very interesting way of realizing an integrator, a non-inverting integrator and a non-inverting differentiator using some very simple circuit tricks. Okay. Something that we have not discussed so far, but it's a very interesting idea. I thought I'll just introduce it to you now. We will revisit it when we talk about oscillators. Let's say you are given a circuit like this. You start with a low pass filter, which is an R and a C, a first order low pass filter, and then just add a negative resistance of value minus R in parallel with the capacitor. Now, what do you think will be the transfer function from input to output? Can you guys solve it? Just apply KCLs and KVLs and see what you get. If you can solve the circuit, see what you get as a transfer function. See, when a circuit is very small, you can use a lot of tricks to solve it. This is a Thevenin resistance, right? Voltage source and a resistance in series is a Thevenin resistance, is a Thevenin equivalent. Convert it to a Norton equivalent. If you convert it to a Norton equivalent, then what do you get? You get a current source of value VI by R. That's like a source transformation. You can convert a source, a voltage source and resistance in series to a current source and resistance in parallel. So you get plus R, capacitor, and minus R. Now, can you tell me what will be the transfer function? What will be the output voltage? V0 by Vi. What will that be? So I have this is a capacitor here and a negative resistance of value minus R. What will be the equivalent of R and minus R? If I put a resistor and minus R in parallel, what do I get? Is that fine? It's like an open circuit. It's an infinite, right? So put R and minus R in parallel. I can remove these two. They both are like an open circuit. R and minus R will cancel out. Now you are left with just a capacitor. So what do I get? VO by Vi for this circuit? 1 by SRC. A current of value Vi by R is flowing into an impedance of 1 by SC. So you get 1 by SRC. So I've achieved a non-inverting integrator by using a negative resistance. Okay. So I have built a circuit which will realize me an integrator whose value is with a transfer function of ideal integrator with a transfer function of 1 by SRC, starting from a passive RC circuit and then just adding a negative resistance in parallel with it. Parallel with the capacitor, you get a non-inverting integrator. Yeah. So how do you realize negative resistance? I'll talk about that. We'll first see how to do it. Then we'll look at practicalities of realizing a negative resistance. I'll come back to that. Now, let's say we start with we'll just interchange the capacitors and resistors. If you do that, now can you guess what will be the transfer function? You can apply the same source transformation theorems. The same source transformation theorems will hold here too. Can you tell me what will be V0 by Vi for this circuit? Apply the similar source transformation theorems. This is a voltage source of value Vi, convert it to a current source. That will be Vi by SC. So it will be by 1 by SC. So it will be SC into Vi, right? So if I have a voltage source and resistance in series, I can convert it to a current source and resistance in parallel. And the value of the resistance will be same as a Thevenin resistance, which is series resistance Rs. And the current source will become, the value will be equal to Vi by Rs. That this current here is the short circuit current. It's the Thevenin to Norton converter, right? Conversion. It's also called source transformation theorem. So I'm assuming you know this, and then apply this here. you will get this circuit can be converted to a capacitor, a current source and a capacitor. Remember, source transformation theorem can be applicable for whatever be this impedance. It doesn't have to be a resistor. It will apply even for impedances. Okay, so if I have Vi and Z, then I can convert it to a current source of value Vi by Z into Vi by Z as a current source and a parallel impedance of value Z. So now I'm converting this current voltage and capacitor in series to a current source of value Vi times SC. So it is Vi by 1 by SC. So you get Vi times SC and a capacitor in parallel. This now comes in parallel with a resistance of value R and another negative capacitance of value minus. So if I put C and minus C in parallel, the total net capacitance will be C minus C, 0, right? Two capacitors in parallel, they will add up to a zero capacitance. A zero capacitance is open circuit. If I put two capacitors in parallel, they are like open circuit. So they'll cancel each other out and you will end up with a circuit like this. So this current will flow through a resistor and you'll end up getting a transfer function of SRC. Okay, I've now realized a first order differentiator, ideal differentiator, using a negative capacitance, starting with a simple passive RC circuit. And with some modifications, I was able to realize a first order derivative, okay, of ideal differentiator. Now, I'm going to generalize this theorem and simply say that if I start with an input voltage source with a series impedance Z1 in parallel, in series with it, and I'll start with this. I'll start with a potential divider network, Z1 and Z2. And then if I connect another impedance whose value is say minus Z1, do that to, connect it to an impedance of minus Z1, then do a similar source transformation. Convert this voltage source to current. You will end up with an impedance Z1 in parallel with minus Z1 and Z2. So this here is your output node. This is your output node. So what will you get? The transfer function for this circuit is Z1, Z2 by Z1. If you recall, both integrator and differentiator, op-amp based integrator and op-amp based differentiator, they were operating on this principle. We just put two impedances and then realized a ratio of two impedances. That's how you got in a inverting integrator. It was the ratio of capacitance to resistance. In an inverting differentiator, it was a ratio of resistance to capacitance. Right? The transfer functions were Z2 by Z1 with a minus sign. So you got minus 1 by minus 1 by SC into R. Okay, Z1 by Z2, Z2 by Z1. That is, I'm calling the feedback impedance as Z2 by Z1. So it will be minus 1 by SC upon R. So you get minus 1 by SRC. And for an integrator, differentiator, it was R with a minus sign by 1 by SC. So you get minus SRC. So I was able to realize ratio of impedances using op-amps. And that's how I was realizing ideal integrators and ideal differentiators. Now, I was able to realize similar ratio of two impedances, provided I have I'm somehow able to realize a negative impedance of value minus Z1, which is the negative of the series the impedance at the input port. Okay, if I have such a circuit like this, then I can realize. Now the question is, how do I realize a negative impedance? That's the question. How to realize negative resistance? There are some practical devices. There are some specific devices which tend to have negative resistance properties. Okay, but for a monolithic solution, such devices may not be feasible. Monolithic meaning we want everything to be in a circuit level solution, which includes MOS transistors, and that's what I want. I want it to be a MOS transistors based circuit. then I can't use some specialized devices like, like you guys said, silicon control rectifiers or gun diodes. I'll not be able to use that. Okay. So yeah, so I'll come to that. So one of you raised a question that if I have an output, let's say I connect with minus Z1 and let's say I put a load resistance ZL here, then am I not loading it? The moment I put a load resistance, then my gain changes. Yes, that's true. So you can put a buffer. So whenever you are this cannot directly drive a load, you can just put a buffer, a voltage buffer, and we will see you don't need to do that. With some realizations, you don't even need to do that. We'll take up two circuits to see how this can be realized. So let's start with, can I use Miller's theorem to achieve negative resistance? You guys know that if I take a impedance of value Z, and if I apply a voltage Vi here, and if I apply a voltage of value minus A times Vi at the other node, so that's what Miller's theorem does, right? You take an impedance, connect between two ports, which are voltage, whose voltages have a relationship. So you take, this is minus A times Vi and this is Vi. Connect an impedance between these two terminals. Then the input impedance is given by Z by 1 plus A. So the input terminal of this impedance, one terminal of this impedance, the other terminal voltage should have a relationship with the input terminal. If I can realize that, then I get an impedance of value Z by 1 plus A. Okay. Now this is true for any value of A, where A can be positive or A can be negative. It doesn't matter. You will get this result. What if A is positive? If A is positive, you will get a relationship, the Miller impedance seen at this input port. So let me show this here. So if I have an impedance Z connected between an amplifier, it's going to, if Vi is the input voltage, it's going to produce a voltage of A times Vi at the other node. Now, if you are interested in finding what is the input impedance, how will you find it? So Vi, I'm interested in measuring the current II. The ratio of Vi by II will be my Miller impedance. Now, if I apply, if this node voltage is Vi, this node voltage is A times Vi. So the current flowing through this impedance, II, is simply given by Vi minus AVI. So that will be 1 minus A times Vi upon Z. So if I divide Vi by II, I will get Z by 1 minus A. Okay. So if I choose A equal to 1, then that will look like an open circuit. There will be no current flowing through this impedance, even if you change this input voltage. It will appear like a unity gain and it will appear like an infinite impedance. If I choose A equal to 2, then I will get a perfect negative impedance. Okay. So if I choose A equal to 2, then I'm going to get a perfect negative impedance. This is what we are going to use to realize negative impedances. The whole idea is, if I can put an impedance between a gain stage such that the gain of this amplifier happens to be 2, then I can, in theory, get an impedance of value, a perfect negative impedance. So how do I do that? Let's take a simple circuit like this. We know that a gain of 2 can be realized using a non-inverting integrator, a non-inverting amplifier. A non-inverting amplifier, so if I apply an input voltage Vi here, this node voltage will be at 2 Vi. Remember, I'm driving this node voltage with a finite input voltage. I'm driving it with a voltage source. So therefore, this impedance at this point will be, because I'm driving it with a voltage source, I'm forcing the node voltage at this point. Okay. So why am I using that word? I'll just talk about it in a few moments. But right now, let's ignore what I said for a few moments and then we'll come back to that. Now, if you see, right, I've just put this impedance between 2 points. This is Vi, this is 2 Vi. So if I look at the equivalent impedance at this point, that will simply be Z by 1 minus 2, which will be minus Z. So I will realize I will get an impedance of value minus Z at this port. That's it. I've realized a negative resistance. Once I've realized negative resistance, what did we discuss so far? Start with a RC circuit like this and put an op amp with a resistance in the feedback path. So this node voltage, we just analyze this circuit. This node, the impedance seen here will be minus R. And this node voltage, if you find the transfer function, let's call this node voltage as VO1. VO1 by VI of S is 1 by SRC. And we just analyze the circuit, right? The equivalent circuit for this entire thing is minus R. So this reduces to a resistor, capacitor, and minus R. And we just analyze this transfer function for this circuit is 1 by SRC. So I have now built a circuit that will realize me an ideal non-inverting integrator, okay, using just a single op amp. So what is the voltage V0? Can you tell me what is V of V? I've derived VO1 by VI is 1 by SRC. What is V0 by VI? See, this is VO1. That happens to be 1 by SRC. What is 2, right? Just 2 factor of 2. Because from VO1 to V0, the gain is 2. So you get 2 by SRC. Okay. So this is how we were able to realize an integrator, non-inverting integrator using just a single op amp by using the idea of negative resistance. So that's one thing. The other thing, the other circuit is an ideal differentiator. So start with a capacitance and resistance. This is a high pass filter. And now put the capacitor C instead of resistor, replace it by a capacitor. That's it. Same way, I just have a capacitor C. One node voltage is, if let's call this node voltage VO1. The other node voltage will be 2 VO1. So the capacitance, effective capacitance seen at this input to ground with respect to ground is minus C. Okay, it will appear like a negative capacitance. Okay. So here, if you see, right, I didn't use the 2 capacitors. I just used one capacitor to build a non-inverting integrator. I just built one. I just used one capacitor. I don't have 2 capacitors here. It's just a single capacitor. Differentiator, yes, we have 2 capacitors, but integrator is just having 1 capacitor. I'm just showing another possible realization of a non-inverting integrator using the idea of negative resistance. That's all. Yeah. So here, in the same way, we have already, see, the goal of this course is to show you the wide range of applications that you can build using op amp circuits. So here I wanted to show you that we can realize negative resistances. And one such application of negative resistance is what we are discussing right now. We just said that using the negative resistance, you can build non-inverting integrators and non-inverting differentiators. Okay, and we realized that we emulated the negative capacitance and negative resistance using op amp circuits itself. Yeah. So now if you see, right, VO1, that since this part of the circuit is something that we have analyzed already, so RC, and this will be minus C. So the transfer function from VO1 to VI is simply equal to SRC. And VO by VI, because output terminal is just 2 times VO1, so it will be 2 times SRC. Okay, so this is a ideal differentiator realized using a single op amp, but using the concept of negative resistance. Okay, so if you look at this circuit, right, if you just directly stare at the circuit here, you will immediately observe that this circuit has 2 kinds of feedback in it. The voltage is fed back at the inverting terminal, the voltage is also fed back at the non-inverting terminal. Okay. And so here, let me remove the confusion here. So this the feedback resistors are R1 and R1. Okay, they don't have to be similar to R. They are just there to give me a gain of 2. That's it. So if this R can be chosen, this ratio of 2 resistors is within your control. You can choose these resistors to be independent of these 2 resistors here. Okay. So now if you see, right, there are 2 paths for feedback. There is negative feedback because I'm taking the output and feeding to the negative terminal. There is also positive feedback because I'm taking the output and feeding it to the positive terminal. So now you have both the feedbacks in place, both negative and positive feedback. When you have both these feedbacks in place, then you have to do a proper analysis and see which feedback is dominating. You'll have to find the beta positive and beta negative. Usually, for the circuit to have a steady state, a stable operating point, you need to satisfy this condition. The feedback beta minus, sorry, let me write it as beta plus and beta minus this way. The negative feedback factor should always be greater than positive feedback factor. Slightly greater. There may be equal, but slightly greater. This condition has to be ensured. Now, if you look at this circuit, let's look at the capacitive circuit. What is the feedback factor in the, let's assume this resistor was not present. If this resistor was not present, what is the feedback factor beta plus? I'm just having 2 capacitors in a potential divider fashion. What will be beta plus? Half. And what will be beta minus? That is also half because it's 2 resistors. So now this is a circuit where both these factors are equal. When both of them become equal, you can't precisely say what is the steady state operating point of the circuit. So anytime your output changes, right, both V plus and V minus are changing by the same amount. Therefore, we know there no signal will be fed back. The net feedback will be 0 because beta plus is equal to beta minus. When that happens, so it's like this. You guys can picturize. Let me show it. Okay. So let's say you have a negative feedback system with a forward path gain A. So you have 2 feedback paths. One is beta minus. This is the negative feedback path. And then you have another feedback path, which is beta plus, which is adding positively to this. For the system to have net negative feedback, beta plus minus should be greater than beta plus. If beta minus becomes equal to beta plus, then what happens? I'll come to that. If beta plus becomes equal to minus beta plus, then these 2 will cancel out and the op-amp will behave as though it is an open loop. So we can't really say the feedback, yes, it is ensuring. Okay. So I'll come to the, one of you asked what will happen to the virtual short condition. I'll come to that. So now if you see, right, what is happening in this circuit is that I have added a capacitor at this node and a resistor at this node. What impact, I'm just adding some impedance, right? Some impedance at this node. What impact will that have on beta plus? Will beta plus be equal to half or will it be less than half? If I put some impedance at this node, say I have a resistor R. Previously, I also had a resistor R at the input. Now I'm putting some impedance cap whose value is C around that node. When I put an additional impedance, that's going to decrease the overall impedance of this parallel RC network. Because that impedance slightly decreases by whatever, but high frequencies, it will become very low. Okay, it will become very low. So it's going to become very small. So your beta plus will become slightly smaller than beta minus. The moment I add a capacitor, that will slightly decrease your beta, the feedback factor. So therefore, we can say, okay, this circuit will still be in negative feedback mode. Also, you can think about it this way. All practical capacitors, the ones you purchase in the market, more electrolytic capacitors, the ones you see in your labs, ceramic capacitors, they will all come with an inherent series or parallel resistors. So you can picturize that you will have some series or parallel resistors along with it, which will ensure that beta minus beta plus will always be less than beta minus. The same logic holds true here as well. The moment I add a resistor here, the positive feedback gain decreases. It will slightly become smaller compared to the positive feedback factor will become slightly smaller than the negative path. So we can still say that this op-amp will be in negative feedback mode. The condition of virtual short, which is V plus becoming equal to V minus, holds true only for negative feedback systems. You need to have negative feedback. Negative feedback and forward path ideal op-amp. Op-amp forward path gain A has to be infinity. If your op-amp gain is infinity, only then, and the circuit is in negative feedback, then this condition holds true. V plus will be equal to V minus. Otherwise, this condition will not hold. Okay. For this condition to hold true, the net, when you have both positive and negative feedbacks, the net negative feedback beta minus should dominate, should be slightly greater than beta plus. This condition has to be satisfied. In a later lecture, probably at some other point, I will take some circuits and talk more in greater detail about negative and positive feedbacks. But right now, because you may get a doubt, okay, there is both positive and negative feedbacks in the circuit, we'll just work it on. So that's why I just gave this explanation right now. Okay, so that's a different way of realizing, different way of realizing inverting, non-inverting integrators and differentiators using the idea of negative resistance.